Now, we're going to talk about LLaVA model. LLaVA, which stands for Large Language and Vision Assistant, is a multimodal model designed to process both images and text. It combines the capabilities of visual processing and language understanding to perform tasks like answering questions based on images, generating captions, and even creating text based on complex images. Let's explore it in 4 parts. The LLaVA model architecture. The multimodal fusion layer handle conflicting visual and textual information. How does the projection matrix work in LLaVA? The differences between projection matrices in LLaVA and Florence VL. Let's break this down. The first. Key components of LLaVA. 1. Vision encoder. LLaVA uses a pre-trained model called clip-vit, which is a type of vision transformer. This part of the system is responsible for analyzing the input image. It takes the raw image data and transforms it into a set of features that capture important visual details. These features are then passed on to other parts of the system for further processing. 2. Language model. The core language model of LLaVA is based on LLaMA, specifically a variant called Vicuna. This is a large language model that processes the text input and generates responses. The language model takes both the visual features, processed by the vision encoder, and the text input to produce a response that makes sense in context. 3. Projection layer. This is a crucial component that bridges the gap between the vision encoder and the language model. The projection layer takes the visual features from the vision encoder and converts them into a format that the language model can work with. It does this by applying a projection matrix that aligns the visual information with the textual input format, enabling both types of data to be processed together. The second, how it all works together. 1. Input image. The system starts with an input image, which is passed to the vision encoder. 2. Feature extraction. The vision encoder processes the image and extracts key visual features. 3. Feature projection. These visual features are then passed through the projection layer, where they are converted into a form that the language model can understand. 4. Text input. Alongside the image, a text query or instruction is provided to the system. 5. Processing by the language model. The language model processes both the visual features, now in the correct format, and the text input. 6. Response generation. Finally, the language model generates a response that integrates both the image and text information. The third. Important architectural features. 1. Modularity. LLaVA is built with modularity in mind, which means it's easy to swap out different components, like the language model or the vision transformer. This flexibility makes it great for research and experimentation. 2. Multimodal fusion. The projection layer is key in fusing visual and textual information. By aligning the visual features with the language model's semantic space, LLaVA can reason about and generate responses that draw from both types of data. 3. Instruction tuning. LLaVA is trained in 2 main stages to optimize its performance. The first stage ensures that the visual and textual features are effectively aligned. The model is then fine-tuned for specific tasks to improve its accuracy and performance. In summary, by combining these components and training strategies, LLaVA excels at tasks that require a deep understanding of both visual and textual information, making it an advanced tool for multimodal tasks. Now let's go over how the multimodal fusion layer in models like LLaVA helps manage conflicting visual and textual information. This layer is designed with several strategies that enhance the integration of multimodal data, making sure the model can effectively reconcile discrepancies between the 2 types of input. Here's how it works. The first. Attention mechanisms. 1. Cross-attention. This mechanism allows the model to focus on the most relevant parts of both visual and textual inputs. Using cross-attention, the model can weigh the importance of specific visual features when processing textual information and vice versa. This ensures that when there's conflicting data, the model can prioritize the most relevant information from each modality, helping it make more accurate decisions. 2. Self-attention. Each modality, whether it's text or image, also uses self-attention. In the text, self-attention helps the model consider the context of words, which is crucial for disambiguating meanings. For images, it helps the model focus on important areas like objects or regions that are essential to the overall understanding of the image. The second, feature fusion strategies. 1. Hierarchical fusion. The fusion layer can use hierarchical fusion, which means it combines features at different levels of abstraction. For example, low-level features, such as edges and textures, are combined with high-level features, like object identities. This approach helps resolve conflicts by giving the model a richer context to work with, allowing it to better interpret the data. 2. Multi-layer perceptron, MLP. In LLaVA, the projection matrix has evolved into an MLP, which helps the model perform deeper integration of visual and textual features. This makes it possible for the model to learn more complex relationships between the two modalities, helping it resolve conflicts more effectively. The third, semantic alignment. 1. Common semantic space. The projection matrix ensures that both the visual and textual features are mapped into a common semantic space. This alignment allows the model to compare visual and textual data more easily, reducing conflicts and helping it better understand the relationship between them. 2. Loss functions. During training, specific loss functions are used to optimize how the model represents both the visual and textual data. These functions encourage the model to minimize discrepancies between the two modalities, further enhancing the alignment and coherence between them. The fourth, contextual reasoning. The fusion layer includes contextual reasoning capabilities, which means the model can take into account the broader context when interpreting conflicting information. For example, if there's a contradiction between a text description and an image, the model can use context from the surrounding text or previous interactions to help resolve the conflict. The fifth, robustness to noise and variability. The fusion layer is also designed to handle the inherent noise and variability in multimodal data. The model uses techniques like dropout during training and robust feature extraction methods, making it more resilient to inconsistencies between visual and textual inputs. In summary, the multimodal fusion layer in LLaVA manages conflicting visual and textual information using advanced attention mechanisms, hierarchical fusion strategies, semantic alignment, contextual reasoning, and robustness to noise. These techniques ensure that LLaVA can effectively integrate and process multimodal data, improving its ability to handle tasks that require a nuanced understanding of both images and text. Now, let's go over how the projection matrix in LLaVA, Large Language and Vision Assistant, works and why it's so important for integrating visual and textual data. The first, purpose of the projection matrix. The projection matrix acts as a bridge between the visual and language components of the model. Since images and text are fundamentally different types of data, they exist in separate spaces. Visual features are quite different from textual representations. The projection matrix transforms the visual features into a format that the language model can understand. This way, the model can process both image and text inputs together in a unified manner, making it possible for the system to reason about and generate responses based on both types of data. The second, feature alignment. The vision encoder, in this case clip-VIT, processes the image and extracts visual features, which we call HV. These features represent various visual patterns, shapes, textures, and objects from the image. However, these visual features are not in a format that the language model can understand. The projection matrix, in W, takes these visual features, HV, and maps them into the same space that the language model uses. This transformation results in ZV, which are the projected visual features. Now, these features are aligned with the language model's semantic space, meaning both the image and text data are in a compatible format for processing. The third, the transformation process. Let's break down the process. 1. Input. The model starts with an input image, which is processed by the vision encoder to produce HV, the visual feature vector. 2. Transformation. The projection matrix W is applied to HV, transforming it into ZV, the new set of features that the language model can handle. Mathematically, this is represented as: here, W is the projection matrix and HV is the raw visual feature vector from the vision encoder. 3. Output. The result is ZV, which now represents the visual features in a way that the language model can understand and work with. The fourth. Integration with textual data. The textual input, let's call it XQ, is passed to the language model, LLaMA. The language model processes both ZV, the projected visual features, and XQ, the text input. The fifth. Trainable parameters. The projection matrix is trained in 2 stages. 1. Pre-training stage. During pre-training, the projection matrix W is the only part that's updated or trainable. The vision encoder and the language model are frozen, meaning they don't change. The goal here is to align the visual features with the language model's word embeddings so that the image and text can be understood in a compatible way. 2. Fine-tuning stage. After the pre-training, the projection matrix W continues to be updated, but now it works alongside the language model. The vision encoder remains frozen. This stage allows the system to refine how the visual and textual information are integrated, improving how the model generates responses and handles multimodal data. In summary, the projection matrix in LLaVA is crucial for transforming the visual features from the image into a format that the language model can process. By aligning the visual space with the textual space, it enables the fusion of both image and text data, allowing the model to perform complex tasks that require understanding both types of input in a unified way. This is what makes LLaVA so powerful for multimodal tasks. Now let's break down the key differences between the projection matrices in LLaVA and Florence VL. These differences primarily come down to the design, functionality, and the underlying vision encoders used. Here's a detailed comparison. The first. Vision encoder. For LLaVA. The vision encoder in LLaVA is CLIP, Contrastive Language Image Pre-training. CLIP is excellent at extracting robust image features, especially due to its use of contrastive learning. However, its focus is more on learning semantic alignments between images and text rather than in-depth visual feature extraction, which can limit its performance on certain vision-heavy tasks. On the other hand, Florence VL uses the Florence 2 model, a generative vision foundation model. Florence 2 captures a wider and richer range of visual features due to its more advanced architecture. This model is designed to be more flexible and adaptable to a wider variety of downstream tasks, which allows it to better capture complex visual information and provide more accurate multimodal understanding. The second. Projection matrix design. For LLaVA. Initially, LLaVA employed a simple linear layer to project the visual features into the language model's space. However, in later versions, this design evolved into a more complex multi-layer perceptron, MLP. This allows for better integration of the visual and textual features, improving the model's ability to handle cross-modal connections. In Florence VL, the projection matrix uses an MLP to project multiple visual features extracted from different levels of the vision encoder into the shared space of the language model. Florence VL introduces an innovative depth-breadth fusion architecture, which allows the model to combine visual features from different depths of the image encoder. This leads to a more sophisticated and nuanced integration of visual information with the textual data. The third. Training methodology. For LLaVA. LLaVA employs a 2-stage training process. In the first stage, the projection matrix is pre-trained, while the weights of the vision encoder and the language model are frozen. In the second stage, the projection matrix and the language model are fine-tuned together. This process allows the projection matrix to align visual and textual features effectively over time. In Florence 5L, the pre-training is driven by contrastive learning. The model optimizes both visual and textual representations to minimize the distance between them in the shared embedding space. The projection matrix is part of this framework, jointly optimizing both modalities for tasks like image text retrieval and VQA. Unlike LLaVA, Florence VL does not train the projection matrix separately in distinct stages. Rather, both the visual and textual representations are learned together. The fourth, performance and adaptability, for LLaVA. While LLaVA performs well on multimodal tasks, the use of CLIP as the vision encoder may limit its performance on more complex, vision-centric tasks, as CLIP isn't as advanced as some newer models. Nevertheless, LLaVA has shown strong performance on a variety of benchmarks due to its effective training strategies and the use of its projection matrix for better multimodal integration. On the other hand, Florence VL shows significant improvements over LLaVA across many multimodal and vision-centric benchmarks. Florence VL benefits from the Florence 2 model's superior visual feature extraction and its sophisticated approach to cross-modal learning, making it particularly strong in tasks like visual question answering, VQA, perception tasks, and optical character recognition, OCR. In summary, while both LLaVA and Florence VL use projection matrices to align visual and textual features, their differences lie in the choice of vision encoder, the design of the projection matrix, the training process, and the performance outcomes. LLaVA uses CLIP and simpler projection methods for multimodal reasoning tasks, whereas Florence VL, with its Florence 2 encoder and advanced depth-breadth fusion technique, offers superior performance across a broader range of vision-centric tasks and multimodal challenges.